we have another special dress-up day. It's Tropical Thursday here at the school where I teach. All that's kind of beside the point, so let's remove all the extra stuff here and move on. So we're going to be looking at how you get the shapes of certain kinds of molecules. We're moving today from sp3 hybridization to sp2 hybridization and to sp hybridization, and look at how molecules get their shapes as a result of all these different forms. So we've covered molecular shapes a little bit already, but we're going to be doing this a little more in detail, okay, and show you the kind of things that you're expected to do in this class. One of the things that I do in this class is spend a little extra time trying to help you figure out molecular shapes, because when you get to college and they expect you to do it, they don't give you this kind of support. Okay, at least in any class I've ever been in, I've never gotten this kind of support. They just kind of, you got to be able to figure it out. There's no, step-by-step process. I have a step-by-step process, and if you are diligent about following this step-by-step process, you're almost always going to get the right molecular shape, even if you're not good at thinking in 3 dimensions. And that's really important, to be able to think in 3 dimensions. But even if you can't, this gives you some support and a step-by-step mechanism for getting it done. Okay, and so we've done this before. But let's start with one we've already done before, and then we'll move on to something else, okay? Let's start with methane. Well, I'll tell you what, let's do carbon tetrachloride. You get the same result, but a little bit different molecule. So we can do something a little bit different, okay? So you need to get out your periodic table if you don't have it already. Get out your periodic table if you don't have it already. And let's figure out how many electron dots, how many electron dots to put around both carbon and chlorine. Okay, both carbon and chlorine. I've got 4 chlorines to work with here. All right. So just to tell you how to do this, in case you've forgotten, the first primary energy level in an atom is not going to be the one that we're dealing with for carbon, because carbon is in the second primary level. We're only interested in the electrons that are in the highest energy level, and we call that the valence level. All right. So carbon's located right here, and we're not interested in the electrons in the first energy level, represented by the position of hydrogen and helium in that first row of the periodic table. Okay, those are not involved in bonding. Only those electrons that are in the highest energy level are involved in bonding. Okay, so carbon is in the second row, so it has electrons in a second primary energy level, what used to be called a second shell. Okay, and so there are 2 electrons in that second primary energy level, represented by the position of lithium and beryllium on the periodic table. They're not the same as the electrons, but those help you figure out how many electrons are there. And there are 2 electrons in the p sublevel, represented by the position of boron and carbon over here in the p sublevel section of the periodic table. Okay? So that's a total of 4 electrons in the highest valence level, the highest energy level, which is the valence level. Okay? Now, what happens is you go through this hybridization we've been talking about. And in hybridization, you don't just have 2 electrons in the S sublevel and 2 electrons in the P sublevel. For this particular hybridization, you have electrons in a new set of orbitals called sp3s. We're going to take all 4 of the orbitals involved and mush them together and spit them out as 4 new orbitals, all equal in energy, all equal in their shape, and arranged in a 109.5 degree angle apart. Okay? So we got carbon tetrachloride here. And what we need to do, since carbon seems to be the atom in the center, okay, because we got 4 chlorines, it seems reasonable they're going to be attaching around it. We'll figure it out anyway. Even if you don't know that, you can figure it out by the process of elimination. Okay? So how many electron dots do I put around a carbon? 4. One on each of the 4 sides. And if we needed more electrons, we pair them up on those 4 sides. Okay? 2 at a time. Pair them up. Okay? On each of the 4 sides. All right. Then chlorine. How many electrons or electron dots do we put around a chlorine using that same process I just described? 7. 1, 2, 3, 4. 1 on each of the 4 sides, and then pair up as needed to get to 7. Okay? But I need 4 chlorines. I've already told you that. You could figure out how many you needed even if I didn't give you 4. But I gave you 4 in this case. So there's a chlorine. And if I take and do the sharing arrangement with just these 2 atoms, I can share these 2 electrons. That would give chlorine the 8 electrons it wants to have. Most atoms, other than hydrogen, want to have 8 valence electrons. That's called the octet rule. Okay? And so this gives because chlorine is sharing this electron with carbon, it gets that electron to count in its 8. So it had 7 to start with, now it has 8. But this carbon now has only 5. So we need another chlorine. Okay, and I can share this electron. You don't have to do it like that, no, but you have to show how you can share electrons in a way that gets all the atoms involved, the number of electrons they actually need in their valence level. Okay? Well, that gets carbon up to 6. And now, by adding another chlorine, we get carbon up to 7. And if I add one more chlorine, now carbon is up to the 8 electrons it wants. Each of these 4 chlorines has the 8 it wants, or they want. And so everybody's, if we personify it, everybody's happy. Okay? Well, of course, they're not alive, so they're not really happy or not happy. Okay? But, we often say that. Okay? Now, using Lewis dots, then, we're going to squeeze the electrons in between the element symbols. And we get this. So the electrons that are on the outside, these are called lone pairs or unshared pairs. You still have to show those. But the electrons that are shared get squeezed in between the element symbols. Okay, so these 2 electrons are squeezed in between here. And that's a Lewis dot formula. All right, we started out with electron dot shape or electron dot formulas, electron dot notation. When we shared the electrons, we now call this whole thing together the sharing arrangement. Now we have what we call a Lewis dot formula. From a Lewis dot formula, we can write a Lewis formula where shared pairs of electrons are replaced with lines pointing from one element to the other where they're shared. So I've only got 2 electrons, 1 pair here between this chlorine and this carbon, so I have 1 line pointing between the chlorine and the carbon. And all the chlorines have 1 pair. Well, I don't want to put an H there. That's supposed to be a chlorine. Still have to have those lone pairs out there, or they're also called unshared pairs. Okay. To find the molecular shape, we're going to go back to this Lewis dot formula. Not the Lewis formula, not the sharing arrangement, although you could use that, but this is the one that really meets all the requirements for the way that I teach it. Okay? And we're going to count the sets of electrons around the atom we're interested in. Now, the sets of electrons are, by definition, that I've defined them as, the sets of electrons are all of the electrons shared between 2 atoms, or the lone pairs around the atom you're interested in. Okay? So for the atom we're interested in, and we're interested in carbon because it's the central one here, we're looking at the sets of electrons. They are category 1, all the electrons shared between this carbon and another atom, and all of these sets are 2, or a pair. Or if I had lone pairs on that central atom or atom of interest, those lone pairs would make up a set. That's the second category. Okay? And what I'm going to do is find a shape, a 3-dimensional shape. Now, this is 2-dimensional shapes. Okay? Our balloon models, when we made methane, was 3-dimensional. If you mashed it down flat, you'd have a 2-dimensional shape, kind of like this. But we're looking at 3 dimensions now. We're going from 2 dimensions to 3 dimensions. Okay? There's a famous little book written called Flatland. If you ever have a chance to read that, you might want to read that. But it's used a lot in the sciences to discuss higher dimensions and what it all means. And they're talking about the difference between things being flat and 3-dimensional and so forth.
I don't know that movie.
No, not the movie. This is it's a book. Was there a movie, Flatland?
Yeah, there's a movie for the book. I watched it.
Really?
Yeah.
I'll have to watch that.
No, don't.
Really? It is kind of depressing, isn't it?
No, it's like. It's
Yeah.
not.
Okay. Anyway, all right, let's go on. Here we go. So what I need to find is a 3-dimensional shape that will get 4 sets of electrons as far apart as I can possibly get them around this atom. And the shape that gets those as far apart as I can possibly get them is called a tetrahedral, where every angle is 109.5 degrees. Now, unless you can do three-dimensional trigonometry, don't try to figure out why. Just know they're 109.5 degrees apart. Okay? Now, that's a little bit beyond high school, right? College, maybe, okay, if you're a math major. All right, so we've got one angle going up. The next one has to be how far apart? 109.5. Now, I can put it on this side or I can put it on this side. Doesn't matter. Okay? I'm going to put it on this side this time. And let's just say that's 109.5 degrees. Okay? So that's more than 90 degrees. 90 degrees would be right here. This would be up and this would be to the side. That's 90 degrees there. This is not 90 degrees. It's less than 120. 120 is kind of down here. Actually, it's almost halfway in between 120 and 90. Okay? Well, no, it's slightly more closer to 120. Okay? And then you have to have two arms over here. One that's coming not flat on the paper, but swinging out toward you, like I'm swinging out my marker here toward you. And we show that by making a triangle shape. That shows that this set of electrons is going to be swinging out toward you. And then the next one has to be swinging back behind. So if I have my marker here flat on the paper, I'm going to swing it back behind like this. Then I'm going to show that as a dotted line. Okay? So we're going to put all those pairs or sets of electrons that are around this atom we're interested in on these arms. And we have a tetrahedral electron pair shape. You have to know how to name it. All these shapes, all these drawings have to have names, and you have to be able to tell me what those names are. So just this part here, that's an electron dot notation or electron dot formula. Okay? Then the whole thing together is called the sharing arrangement. Just this part right here, Lewis dot formula. Just this part here, Lewis formula. This is now an electron pair shape, but it has another part to the name. It's called a tetrahedral electron pair shape. Okay? Electron pair shapes have only electrons around the periphery in 3 dimensions. Okay? From the tetrahedral electron pair shape, we have to go to the next shape, which is to replace any shared sets of electrons on this periphery here with the element they're bonded to. So all 4 of these sets that I've represented here, all 4 of these sets of electrons are shared with chlorines. So I'm going to redraw this exact same drawing. I hope you're doing this in pencil. I'm going to draw this exact same drawing with all the angles just so. Okay, and I'm going to put those electron dots on there so it's exactly the same. Now, I have you do it this way because I found this is the surest way that students get it right. Students skip steps, they get it wrong. Okay, if you want to take a chance on getting it wrong, you know, and improve your odds of failing the test, that's up to you. Okay? And by the way, this comes back again. Chemistry is a very cumulative subject. We'll be doing the same stuff again when we're trying to figure out when molecules are polar. All right? Or not. Okay? So, you know, do it the way I teach it. It'll help you a lot. All right? So I put all the electron dots around here, and I'm going to replace all the electron dots that are shared in this drawing with showing how they're shared here. Now, sometimes we're going to have lone pairs. In this case, we don't have any lone pairs, but sometimes you do. So we're going to put chlorines where these electron dots are located on all these corners. Okay? And we don't have any electron dots left. Okay? So now, the name of this 3-dimensional shape here was a tetrahedral. This is the same shape because I haven't gotten rid of anything. I just replaced the electron dots. So this is also a tetrahedral. But because I don't have any electron dots left, this is now the molecular shape. So this is a tetrahedral molecular shape. Okay? So if I ask you what is the shape of a carbon tetrachloride molecule? Tetrahedral. That's the molecular shape of a carbon tetrachloride. Does that make sense? Anybody have any questions about that? Yes?
Would you like to guess at that question?
So if you have a 4 here, yeah, it's a good guess you've got a tetrahedral. Okay, in any formula like this, one element, 4 elements, or 1 atom, 4 atoms, you're probably going to have a tetrahedral, but that's not always true. It might be true in high school chemistry where we don't get into hybridization any higher than sp3. But there are sp3d1s and sp3d2s that you get into in college, and if you go into higher levels in college in certain areas, you might get an even higher types of hybridization. Okay? But that's about as high as you get in most college classes, that I'm aware of anyway. All right, so that's how you do this. Now, how do we know this is sp3? How did I know this is sp3? Because carbon had to hybridize 4 orbitals to get 4 single bonds. How did I know it's sp3? Carbon had to hybridize 4 orbitals to get to 4 single bonds. Single bonds are always hybridized, or always come from hybridized orbitals. They are always sigma bonds. Okay, sigma bonds have to come from hybridized orbitals. All right, if you know that stuff, the rest of this you can figure out. Okay. When you have double bonds, then hybridization has to back down from that sp3, from 4 to 3 hybridized orbitals. So to have a double bond, you would have sp2 or sp in one case. Like your homework last night was, we had one atom that had an sp hybridization and 2 atoms that had an sp2 hybridization. We'll get to that. Okay. All right. Then let's do. How about nitrogen trichloride? Let's do nitrogen trichloride. Okay, I'm going to let you guys, I'm going to pause the video here, and I'm going to let you guys figure out the Lewis dot formula for nitrogen trichloride using the system I've taught you. All right, we're going to move along here pretty quickly, okay? So follow with me. Hopefully you've already got this. Everybody said they did. So nitrogen has 5 electron dots. Chlorine, we already know, has 7. We can share electrons here, and here, and here, and this gets the nitrogen and the chlorines up to the 8 valence electrons they want to have. The Lewis dot formula then looks like this. Okay? And I didn't ask you to draw the Lewis formula. In fact, you don't have to have the Lewis formula to do the rest of it, but it's a good thing to know because you need to know what the Lewis formula is. And for that, we're going to replace any shared sets of electrons with single lines pointing from or going from one element to the other element that they're shared with. And the lone pairs have to be there. The unshared pairs, these double dots here, are the unshared pairs, or also called lone pairs. Okay, and then for our three-dimensional drawings, we're going to look and see how many sets of electrons we have around that central atom. Okay, and they're the same number around the central atom as they are up here with our other drawing. Okay, there's 4 sets of electrons. Well, that's easy. We must have a tetrahedral. Yeah. Lone pairs count as a set. You're looking for all the sets of electrons around that atom you're interested in, and that includes any shared sets, and lone pairs also make up a set. So we have a tetrahedral electron pair shape. You have to have the name and be able to write that name for me, tetrahedral electron pair shape. So the next step then is to redraw exactly the same drawing in pencil. You're going to put those electron dots out here, so we're not drawing exactly the same drawing. Okay, I got a little stray mark down here. Nobody can be confused by this. That doesn't have anything to do with what we're doing. And now I'm going to replace any sets of electrons down here that are shared up here. And out of the 4 sets of electrons, 3 of them are shared. And you can replace them in any one of those 4 positions. You can put it here, here, and here, or here, here, here. Okay? Doesn't really matter. So when you draw these, you can't draw 90 degrees and expect me to know it's 109.5, okay? But if it's not 109.5, that's okay. It doesn't have to be exactly 109.5. Mine very often are not exactly 109.5. But it needs to be more than 90. And just so we're clear, this is 90 degrees. Everybody should know what 90 degrees looks like. Okay, and 120 degrees is like this. So your angle needs to be between this angle and this angle. Okay? Don't make it too big. Don't make it too small. That is to say, the angle. Okay? Now I'm going to replace 3 sets of electrons. And it doesn't matter which of these 3 you change, but for me to show you what the name of this is when we get to the molecular shape, I want to put them down here on the bottom and leave the lone pair up here. Okay? So the lone pair that's right there, I'm going to leave at the top. You don't have to have it on the top, but that's where I'm going to leave it. Okay? The chlorines are going to go here, here, and here for me. Again, it doesn't matter where you put it as long as you have a lone pair on here. Okay? Now then, the next step is to redraw this exact same drawing here again. Okay, and the last step then, in this, well, first of all, let me tell you this. This is, right here, a modified electron pair shape. So it's a tetrahedral modified electron pair shape. In the previous setup here, we didn't have a modified electron pair shape because we didn't have any leftover electrons. Here we have leftover electrons, and that's a modified electron pair shape.
So you just do the same thing.
Mm-hmm.
You just do the same thing.
I drew exactly the same thing, but this last drawing here, once we get to this, we're going to erase any lone pairs. And we finally get to what's called the molecular shape. Okay? Now this is no longer tetrahedral, because a tetrahedral has to have 4 arms around that atom of interest or central atom, as the case may be. Okay? Sometimes it's the central atom and sometimes it's the one we're interested in. Okay? Now, this is not a tetrahedral because that 4th arm is missing. Okay? Well, let's see if we, I'm going to draw this out, kind of show you, this is, I'll tell you what, let's do it a little bit differently. I got a better way to do this. You might be able to see the difference if I do it this way. What does that look like? It's a pyramid, but most pyramids have 4 sides, right? That makes sense? That's like a 3-sided pyramid, okay? Which is where we get the name from. So, here's our molecular shape that we just drew. This is just a line drawing that connects all of the atoms in this shape. Okay? Yes. Yeah. Okay? And all I'm doing is showing you this so that you can get the idea of what the name of this shape is. All right?
So you just connect them all together?
I'm connecting them all together. Okay? So the name of this shape, whether you're using this shape or this one, because this is the same thing as that, we just turned it over a little bit. Okay? These are looking down on the, this is like looking down on the top, this is like looking up from the bottom. But this is a trigonal pyramidal. Trigonal pyramidal shape. Okay? And it's trigonal pyramidal because it's a 3-sided pyramid. This is called trigonal pyramidal. Okay, trigonal pyramidal, from which that's the name we get. But now that we've gotten rid of all the lone pairs, this is now a molecular shape. So a molecular shape you get once you get rid of all of the lone pairs. Okay? Yes?
No matter what side, even if
So the question is, what if I were to keep the lone pair down here and put a chlorine up here? Or keep the lone pair down here and put a chlorine up there, okay? Well, it's still going to be trigonal pyramidal. It's just a little bit harder to see the shape if you do it that way. You can know that, and you might be able to see it. If I were to leave the lone pair, let's say, down here, my molecular shape would look like this. And that's still trigonal pyramidal. Does that make sense? If I were to put the lone pair here, and all these other arms are going to have the chlorines, then my molecular shape would look like this. And while that's trigonal pyramidal, it's a little harder to tell that's what it is, because you're kind of looking down on it from the sky. Okay, that makes sense. You're looking down on it not from directly above, but kind of at a slight angle over here. You might be able to see that. That might be something that's hard for you to recognize, you know, but that's okay. You just need to know 3 arms that are not equally spaced is going to be trigonal pyramidal. Okay, and when it's pushed back behind the paper, like this dotted line shows it being pushed back behind the paper, that means it's not going to be equally spaced anymore. These are still 109.5 degree angles. Okay, equally spaced would be 120 degrees between each angle. All right. Okay. Let's do another one here. Let's see. Have we looked at the actual shape on paper of water? We did a model of it. Did we do drawing of it? We did. Okay. Then just for practice, let's see. Let's do this one. Okay. I'm going to let you do this. See if you can get all the way to the molecular shape. And then I'll come back behind you and see how you did. All right, so here are the names of all these drawings and what the drawings actually look like. Okay, so we started out with electron dot formulas, okay, and then we became a sharing arrangement when we shared those electrons. Here's the Lewis dot formula. Now your chlorines could be don't have to be on this side and down here. They could be over here at the top, okay, as long as you only have 2 chlorines and you're sharing electrons properly. It doesn't matter which of these sides those chlorines are located on. Here's your Lewis formula, okay, and again, the chlorine could be over here or up here. You can put it in a lot of different ways, as long as you have 2 lone pairs on the sulfur and 2 bonds going to chlorines around that sulfur on the 4 sides of the imaginary square around that sulfur. Then from the Lewis dot formula, we get the tetrahedral electron pair shape. There are 4 sets of electrons around this atom of interest here, this sulfur. So the only way you get 4 equally spaced around that central atom is a tetrahedral, where the angles are all 109.5 degrees. So that's called a tetrahedral electron pair shape. And then you get a tetrahedral modified electron pair shape when you replace 2 of those sets of electrons with the chlorines, because that's what's shared up here. 2 of those sets of electrons around this central atom are shared with chlorines. Then finally we get rid of that lone pair, or these 2 lone pairs over here, and we get a bent molecular shape. And your bent molecular shape might not look like mine. Your bent molecular shape might be this. And that's still bent, okay? And the difference between that drawing and my drawing is that my drawing looks like this, and this drawing you take and spin it around like this. Okay? That makes sense? Now, you might not be good at seeing that in 3 dimensions, but there's the difference, okay? That's my drawing, and that's the drawing, the second drawing there, okay? Got that? One of the problems you did in this class, in this particular year, for homework was formaldehyde. F-O-R-A-L-D-E-H-Y-D-E, formaldehyde. And somebody asked about what this is. They've heard this before. Yeah, it's the stuff you store, most of the time, you store dead animal parts in, okay? So if you see in a biology classroom somebody's got some kind of liquid with a cow brain in it or something, well, that's formaldehyde, most likely. You can store it in other things, but that's the one that's most effective. And the formula for that was H2CO. We did a balloon model for this. And if you're watching this video, we haven't done it yet. You will be doing a balloon model for it, because I almost always do balloon models for formaldehyde. And so we're going to go with the electron dots, the electron dot formulas for the hydrogens, and the electron dot for the carbon, and the electron dot for the oxygen. And then from those electron dot formulas, you share the electrons, get the Lewis dot formula, and then we're going to go to the 3D formulas. Okay, so let's get at least through. I want to let you stop the video, pause the video, and let you do the Lewis formulas, both of the Lewis formulas. So do the sharing arrangement, Lewis dot, Lewis formula. If you think you can figure out the 3D formulas, go ahead, but we're going to do it all for the class here in just a moment. So here's the sharing arrangement. Started out with the electron dot formulas. Now we have a sharing arrangement. I hope you're writing these on your paper when you do it so you can practice, kinetically practice, the names or naming of these things. So that's the electron dot, the sharing arrangement started with electron dots, now it's sharing arrangement. This is the Lewis dot formula. Here's the Lewis formula. Now it doesn't matter if the oxygen's over here, it could be down here. The hydrogens could be on this side instead of over where the oxygen is. Okay, as long as you have around this carbon a pair of electrons here and a pair of electrons and a double pair for a double bond, and that you have the right atoms attached to that, and you have the lone pairs on the oxygen. It really doesn't matter otherwise which of the 4 sides you put those electrons and element symbols on. Now, when we get down here, then there's only 3 sets of electrons around the central atom. A set is either lone pairs, or that's one category. Lone pairs is one category. The other category is all electrons shared between any 2 atoms. So between this atom and this atom, there's 2 electrons. Between this atom and this atom, there's 2 electrons. So these 2 sets have 2 electrons. But this set between the carbon and the oxygen has 4 electrons. It still makes up a set. And since I have 3 sets, I need to get 3 sets as far apart as I can possibly get them. That's 120 degrees. All right, since I have 3 sets then, 120 degrees apart, 3 arms, that's what I need. That's as far apart as I can possibly get them. I'm going to put the electron dots on there. So one of these 3 arms needs to have 4 electrons. I'm just going to put it down here. It doesn't matter. That could be up here or over here. But in this case, I put them down here. Okay? So now this is not a tetrahedral. A tetrahedral has 4 arms equally spaced. This is 3 arms equally spaced. Okay? And that's trigonal planar. It's not in a pyramid as we did on a previous molecule. Okay, this was a pyramid because it kind of puckers up or sticks up a little bit. This one's flat. This is a trigonal planar shape. So we don't care about the lone pairs over here on the oxygen, okay, because that's not the central atom. That's not going to govern the shape of the molecule. What governs the shape of the molecule is the atom to which all these are bonded to. So this is our atom of interest here. Okay, for these simple molecules, it's almost always the central atom. When we get to more complex molecules, we won't have to do those in here. But when you get to college and have to do more complex molecules, or maybe you'll take organic chemistry and you have to do more complex molecules. And we do have an organic chemistry class here. Then you have to, and in fact, I think in biology too, they also do more complex molecules. So you have to know how those shapes actually come out. That's why chemistry is a prerequisite for biology too. the lone pairs in the sulfur govern the shape of the molecule overall. It changed this from being like maybe a straight line or a 90-degree angle to this bent shape. Okay, so in this case, the lone pairs are on that atom of interest that governs the shape of the molecule. Down here, the electrons that are lone pairs over here on the outside, those aren't changing the shape of the molecule in any way. It's only the electrons that are around this atom here that governs the shape of the molecule, because it governs the angles between more than one bond. Okay, so this is trigonal planar electron pair shape. Make sure you can name that, okay? Now we can put the atoms on here where any electrons are shared, but you're going to redraw exactly the same drawing, okay, with the electron dots on here. All right, so it's exactly the same drawing again. But now I'm going to put the atoms on there and replace any of these electron pairs or sets that are shared. And in this case, all of them are shared. All three sets are shared. So I'm going to put a hydrogen here because the hydrogen needs a pair of electrons. This hydrogen needs a pair of electrons. But where I have the 4 electrons in the double bond, that's where the oxygen goes. Now I'm going to erase all those electron pair marks. Okay? And so this is, we don't have any electron pairs left on that atom of interest. So this is not modified because there's no lone pairs left. This is now the molecular shape. It is trigonal planar. I should have put that right in there. So this is a trigonal planar trigonal planar molecular shape is what this is. Okay? All right. You ready to do one more? Well, whether you're ready or not, we're going to do it. Ready or not, here we come. Yeah, we are. Hide and seek. Anybody here at ROTC? ROTC? Oh, wait a minute, we can't do that one. Okay, here we go. Let's do, how about HNO? HNO. Okay? To my knowledge, this doesn't actually exist, but it's a good example of what I want you to see. HNO. Look at how to draw the shapes of molecules that have an sp2 hybridization. So let's see, we did one of these models as a balloon model. I think we did formaldehyde, did we not? And that's H2CO. Okay. If you're writing it, if you were an organic chemist, you'd probably write it COH2, because carbon almost always comes first in an organic system. Okay, and that all goes back to what IUPAC has to do with, what it designates. Well, not really, because organic chemistry is based on the structures that you get from carbons, and we'll get to that later, okay? And that's why I usually write the carbons first. Anyway, so what we're going to do is we're going to start with, let's look at the orbital notation for a carbon before it does any hybridization. We've gone over this before. We're going to go over it again just to make sure we're as clear as we can be. So the first level electrons, those don't change. And this is 2s. This is going to change when we go to the hybridization. And then we got 2p, and we got 2 electrons in 2p. Okay? And so when you do sp2 hybridization, then you only hybridize one of the the only s orbital in the valence level. The valence level is the highest energy level. So we're only going to hybridize this valence level s sublevel. And two of these three p sublevels in the valence level. Now the valence level isn't always 2. It depends on what atom you have. Whatever the highest energy level is, that is the valence level. So if we're only going to hybridize one s and 2 p's, then that means we're going to be just hybridizing these orbitals here. And we're going to leave this p orbital here unhybridized. Okay? So when we show the hybridization using orbital notation, we do it like this. Remember, the lower level electrons don't change. It's only the upper level, the valence level, that changes. We're going to make 3 new orbitals, okay, that all have the same shape and energy. And that's an sp2 because it came from 2 p orbitals and 1 s orbital. And that's in the second primary level. Then we have a p orbital in that valence level that's not changed. We go and count all the electrons that exist in the valence level, and there are 4 of them, and we're going to put those 4 electrons in all these orbitals, one at a time, and come back and pair them up if we need to. 1, 2, 3, 4. Okay, and that's the hybridization, or one way to represent the hybridization for carbon when it has an sp2 hybridization. Well, having this p orbital over here that's unhybridized then allows us to do what's called a pi bond. But let's do the same thing for oxygen, because it also has to have an unhybridized p orbital to create a pi bond, because the pi bond is going to exist between the carbon and the oxygen. So the original ground level unhybridized orbital notation for oxygen looks like this. How many electrons do you have in the p sublevel of oxygen before it hybridizes? Not in the p sublevel. You have 6 total in the valence level. How many in the p sublevel? 4. You need to know this. Now, if you don't remember how to do that, guys, get out your periodic table and figure it out. 1, 2, 3, 4. That's your valence electrons in the p sublevel. Then you also have the 2 over here that are represented by the position of lithium and beryllium. These are not electrons here on the periodic table. But if you use this as a guide to figure out how to write orbital notations or electron configurations, then the position of these elements on the periodic table can tell you how many electrons a particular atom has in its various energy levels, including this higher energy level, this highest energy level called the valence level. So there are 1, 2, 3, 4. And so we paired it up just in the p sublevel here after we filled up all the p sublevel orbitals. And then when we hybridize into sp2, lower levels don't change. We're going to hybridize 1s and 2 p's. Okay? And that leaves us a p orbital that's going to be unhybridized so that we can create a pi bond. We're going to have these 3 orbitals here changed into the same shape and orientation and energy. And this is sp2. We're in the second primary energy level, so we're going to put a 2 out in front. And we have a 2p orbital out here on the end that doesn't change. We're going to write it out here separately. Okay? Again, we're counting all the electrons in the valence level and putting those electrons in all these orbitals, one at a time and pair up where you need to. And there's 6 electrons in that valence level. 1, 2, 3, 4, and then pair up 5 and 6. Okay? So these are sp2 hybrids we've created, so we're hybridizing. Oh, I misspelled that. That's not good. Hybridization. Gracious help me. Okay, there's what we have here. Okay. Whoop. All right. And so S, see if I can do this one right the first time. Okay. All right. So what we've done is we've arranged now the carbon and the oxygen so that they can share one electron in a hybridized orbital. These are all hybridized orbitals. These are all hybridized orbitals. Oxygen has one hybridized orbital that it can share an electron with carbon, or with which it can share an electron with carbon. And so we can create a sigma bond between this oxygen and the carbon. There's also 2 other hybridized orbitals available to do a sigma bond with the 2 hydrogens we need to make a bond with. Okay, and then we've got this p orbital over here that's unhybridized that is going to share an electron between the carbon and the oxygen in what's called a pi bond. Okay, so the pi bond is surrounding the sigma bond. The sigma bond is always directly in a line between the 2 nuclei of the 2 atoms involved. So how did I know that I needed to have a p orbital that's unhybridized and that I needed an sp2 hybridization? Well, Lewis dots can help you figure that out. Okay, and we've done this before, but if we start with the Lewis dot formula, or the electron dot formulas for these atoms, well, this should be carbon here. Oop, I put 1 extra electron on there. That's not good. Because we need 6 valence electrons. Okay? And we share the electrons. So these are all electron dot notation or electron dot formulas. If I'm asking you to do this on a test, you need to label this as an electron dot formula. If I ask you to write the electron dot formula, you need to be able to write these formulas. Okay? So let's see. I'm going to share electrons here. I'm going to share electrons here, and I'm going to share an electron here and here, and then I can share another electron here so that I get a double bond here. Okay? Write our Lewis dot formula now. Okay? So this then is a double bond. For a double bond to happen, I have to have a sigma bond and a pi bond. Okay? So if we were doing balloon models of this, and I gave you this template to help you draw these things if you're not good at it, okay? So I'm just going to do right now, just the double bond. I'm going to ignore these hydrogens over here and these lone pairs on the end. Everybody with me? Just going to show you the double bond to show you why we need a p orbital that's unhybridized to make a pi bond, okay? Just to remind you of that. So the first thing we need, you always have a sigma bond. If there's a covalent bond between 2 atoms, there's always at least one, well, there has to be a sigma bond, period. Okay, there's always one sigma bond in any covalent bond. Always one sigma bond in any covalent bond. Always one sigma bond in any covalent bond. All right, so this is my drawing for a sigma bond. So I'm going to put it under the paper here to use it as my guide. Put it right here in the middle, I guess. And so here's a sigma bond. Okay. And we're looking at the carbon being on one end and the oxygen being on the other. Okay. So that takes care of 2 electrons. You can only put 2 electrons in any covalent bond. Well, if you call it a double bond, there are 4 electrons. This would be 4 electrons in a bond between carbon and oxygen, but there are actually 2 bonds within that bond. Does that make sense? two kinds of bonds within that bonds. So what I'm saying, what I really should be saying here is you can only have two electrons in an orbital. In the same region of space, you can only get two electrons in that same region of space because you can only have two opposite spins, which is also called quantum entanglement. You can only quantumly entangle two electrons. You can't quantumly entangle three. Okay, only two. So you can quantumly entangle two electrons. That means they have to be in this space. So the next pair of electrons here has to be somewhere else other than this. Okay, and for that then we're going to have a pi bond. Now that starts with unhybridized p orbitals. Remember the p orbitals have the double balloon shape. Okay, p orbitals have double balloon shapes. We did that in this unit and the previous unit. We have models. We did balloon models of p orbitals. Okay, but those are going to reach out to each other across the top and the bottom. You can think about this as the hot dog wiener, and this is going to be the bun. The bun has two parts, right? Okay, so here's the illustration I give you on your template for a double bond if you just have one pi bond. Okay, this is both two parts of one pi bond. Okay, so I'm going to slide that under there. Okay, you can see how this p orbital became joined together. This node on the top, this node here on the top of this p orbital, this node on the top of this p orbital joined together, and so does this node on the bottom down here do the same thing. Okay, and now because I'm doing things in pencil, which is what I ask you guys to do, I can erase the p orbital because it pretty much is, well, it's all there, but it's all part of this pi orbital, this pi bond. The p orbitals became a pi bond. And pi, by the way, is the Greek letter for p. Okay? So I have a double bond here, but if you're not thinking this through, if you're not paying attention, waking up, focusing on what's going on here, waking up, focusing on what's going on here, you'll think this is three bonds. This is not a triple bond. This is a double bond. You've got a sigma bond here, and this pi bond is in two parts. Two parts, one bond. Okay? Our hybridization was sp2 on both the carbon and the oxygen in this case. And these came out of p orbitals here on both ends. Okay? P orbitals have two nodes. So this is one node, this is another node. This is one node, and this is another node. So this pi bond has two nodes. Actually, the sigma bond has two nodes. We just don't see it because it's a little more complex than I want to get into in high school chemistry. Okay? So we've got two nodes that actually can be seen when we're drawing these out. Everybody got that? All right. Hearing no objections, I'm going to go forward. So this is why we need this unhybridized set of p orbitals over here. Because without the unhybridized p orbitals, this pi bond can't happen. And we can't have a double bond. Because the electrons can only two electrons can be in the same region of space. To get four electrons between these two atoms, I've got to put two electrons in this region of space and two electrons in this region of space. Okay? Any questions about that? Now let's look at how this gives us the shape of the molecule, because this is just the shape of the bond. Okay? When we talk about the shape of the molecule, we're not so much worried about the shape of the bonds then. So we've got two different things to think about at the same time. Two different things are going on at the same time. Okay? We have a shape of bonds and a shape of a molecule. And you need to know the difference between the two. So if we're going to go with the shape of the molecule now, we're going to look at this Lewis dot formula, and we're going to count the sets of electrons around the central atom, or the atom we're interested in. In really large molecules, there are a lot of central molecules, central atoms, a lot of atoms of interest. And so you have to figure out the shape around all of those to figure out the shape of the molecule itself. But we're just doing simple stuff here. We're looking at what atom that's here that's going to govern the shape of our molecule. Okay? And I can see I have three sets. Now let me define again, for about the fifth time, what a set is. There's two categories of sets. One category is any lone pair around your atom of interest is a set in this context. Okay? Category number two, any set of electrons, whether it's 2, 4, or 6, any set of electrons shared between two atoms makes up a set. So this is a set of 2, a set of 2, and a set of 4. So a total of 3 sets. There are no lone pairs around this carbon. That's the one we're interested in here because it's the one that's going to govern the shape of our molecule. But we have 3 sets of electrons around this atom, and so that's going to govern how we figure out the shape of the molecule. We're going to do everything around that carbon. Okay? So here's our carbon to figure out how to draw the 3-dimensional shape of that molecule. I need 3 sets of electrons, so I need to get them as far apart as possible as I can get them, as far as I can get them from each other in 3 dimensions around that carbon. So this is where you have to use the movie in your head. Okay, you have to use your imagination. You know those video games you guys play all the time? You have to run one of those in your head. Okay? Can you do that? Are you that creative? You should be, because you're at this point. Yes, you are. You're at the point in your mental development where this is easier for you to start doing now than any other time in your life. If you don't start doing it now, then when you're 30, you won't be able to do it. Well, I shouldn't say you won't be able to, but it's going to be a lot harder. Okay? When you learn to do this kind of thinking, processing, problem solving, modeling in chemistry in your head now, where your brain is, if you could put it this way, sort of supple, all right? Before the calcified neuron paths establish themselves really, really strongly, then, you know, you're developing the ability to do this. You're not going to be able to do it at 30. Once you do it when you're a teenager, then you can do it at 30 a lot better. Okay? So it's really critical that you allow yourself and you drive yourself and you push yourself to do this because you're going to be expected to do it. Go to college, they're going to expect that out of you. Okay? All right. So I need 3 sets of electrons as far apart as possible. I want you to think. I've got a 360-degree circle here around this carbon. Okay, 360 degrees. But I've also got a 360-degree circle that goes this way. And a 360-degree circle that goes this way. Okay? That makes sense? In all of those circles, what's the furthest I can get these 3 sets of electrons? 120 degrees. 120 degrees is as far apart as I can get from each other. And that came from the guy who claimed he can't do this kind of thinking. He was just saying, back there, but he can do it. Okay? Of course, I've told you that before, but you can do it. You can. What's that movie? You can do it. Okay. All right. 120 degrees. All right? That's as far apart as you can get them. Okay? And 2 of these have a pair of electrons. So 2 pairs. And this set of electrons down here is 4. Okay? Does that make sense? That's our first 3-dimensional drawing, and it's kind of flat. Okay? It is 3-dimensional, but this 3-dimensional just happens to be also flat. Okay? And so we call this trigonal because it's 3-sided. If you look at the really old pictures around the time of the American Revolution, people wore 3-cornered hats. You ever seen those pictures?
Yeah.
You know, those pictures of paintings of, what's his name, Paul Revere. He wears a 3-cornered hat. Okay, well, trigonal is 3-cornered, basically. Okay, so it's trigonal planar because it's flat. Trigonal planar, and the type of drawing it is. This is the geometry. The type of drawing it is, what we're showing here is called the electron pair shape. All right? Trigonal planar electron pair shape. Now, the next step that we've always done, all those drawings we did in the previous lesson, we always went next and replaced any sets of electrons with the atoms if they are shared. So it looks like this. We draw out exactly the same shape again. Everything here. Actually, I shouldn't be putting the dots on there in pen because I need to erase them in a minute. Okay? All right? And then we're going to go back up here and say, okay, this pair of electrons, that's shared between this carbon and this hydrogen. So I need to put a hydrogen here. This pair of electrons is shared between this carbon and this hydrogen. I need to put a hydrogen here. This set of 4 electrons is shared with an oxygen, so I need to put an oxygen here. Okay? And then we can go back and erase any lone pairs, or you can erase the lone pairs as you do it, whatever works for you. Now, since there are no more lone pairs, this is your clue. This is your test. If there are no more lone pairs, you've got a molecular shape. If there are lone pairs left, then you've got a modified electron pair shape. Okay, but this is the molecular shape. We're going to be done with this when we label it. Oh, you're right. Thank you. I just said that, and now I'm writing the wrong thing. Good catch from the guy who said he can't think. All right. Trigonal planar electron pair, molecular shape. Okay. All right. Yep. Okay. Got that? Any questions about that? Huh? Yep.
Why aren't the dots on the O's?
These dots?
No, on the O's.
Oh, we don't have to show it when we're showing the shape of the molecule. When we get to the final shape of the molecule, those, what we're looking at is the shape around this atom here. That's really what's critical. I mean, they're there, but because they sit out there and they're not bonded to anything here, okay, then they're not really changing the shape of the molecule at all. Okay? Good question, then. Any questions? Any other questions? All right, then. Let's give you one to try. All right. Now, if you ever try to look this up, I don't think this actually exists, but it's a good example for you to practice with, okay? So I'm going to pause the video here, let you guys work on this for a minute, and then I'll come back behind you and show you how it's done. All right? And you can check your work, see if you did well, or if you need a little more work. Okay, let's see how you did, guys. First thing, you need electron dot formulas. Okay, then we need a sharing arrangement. Need a Lewis dot formula. You don't really need a Lewis formula to get to the shape, but I want you to draw the Lewis formulas just so I know you know how to do it. Lewis formulas, those are going to be even more important later. From this shape, then we're going to count the sets of electrons around a central atom. I see I have 3. So I need a trigonal planar shape. I've got 2 dots on right here between this hydrogen and this nitrogen. Got 2 dots up here that are by themselves. That's a lone pair, but they have to be here because a set includes the lone pairs as well as all the electrons shared between 2 atoms make up a set. And there are 4 electrons here. So this is a trigonal planar electron pair shape. Then I'm going to redraw exactly the same shape with all the electron dots on here. And I'm going to go through this drawing, this Lewis dot formula, and very carefully replace any sets of electrons that are shared. Well, this set of electrons is shared between hydrogen and nitrogen. So I'm going to put a hydrogen here. This set is not shared, so I'm going to leave it alone. This set of 4 is shared with oxygen, so I'm going to put that down here. Okay, and so this is a modified electron pair shape, and it's still trigonal planar. Okay, so trigonal planar electron pair shape, trigonal planar modified electron pair shape, and the next thing is to redraw this exact same drawing in exactly the same orientation and do it in pencil. And then you can erase your lone pairs, and if there are no more lone pairs, that must be the molecular shape. So this is a bent molecular shape. Just like water was bent, we started out with a different beginning structure than we did with water. Water started out as tetrahedral. This starts out as trigonal planar, but we both of them allow you to end up with a bent molecular shape. Okay? Got that? All right, then let's talk about triple bonds. Okay, this is called hydrogen cyanide. Okay, dangerous, nasty stuff. Well, I think if I'm not mistaken, this is the gas they used to use in the gas chamber to kill people, to execute people. Okay, cyanide is a really nasty stuff. Sodium cyanide, potassium cyanide is used in rat poisoning, for example. Huh? What now? Oh, there's a thing called the lethal dose. Let's see, 50, LD50, which means that if 100 people were given this amount of cyanide, 50 people would die. I don't know what that is, but if you look it up on the MSDS, it'll tell you. Huh? I don't know. Let's move on and do the shape of this thing, okay? Got it? All right. So then we got hydrogen with a 1 electron dot, carbon with 4, nitrogen with a 5. Go to the sharing arrangement. I hope you guys are getting this so that if I kind of speed along, you're following along anyway. Okay? At this point, we've been doing this a lot. You should be able to kind of keep up with me here. All right? And so this is our sharing arrangement. Then we have a Lewis dot formula. And we've got 6 electrons shared between carbon and nitrogen with 1 lone pair over here on the nitrogen. Okay? 6 electrons shared, you put them in between like this, in this arrangement. Okay? And while we don't need a Lewis, this is the Lewis dot formula. We started out with electron dot notation. We have now a sharing arrangement after we shared the electrons. This is a Lewis dot formula. And then a Lewis formula would replace any shared pairs of electrons with single lines. So there's 3 lines here because there's 3 shared pairs here. We don't really need this to go to the 3-dimensional drawing, but I want you to be able to do the Lewis formulas. And so we need an arrangement that gets this set of electrons and this set as far apart from each other as we can. This set here has 6 electrons, but a set is all the electrons shared between 2 atoms. That's one category, and the lone pairs around that atom of interest are also a category. We don't have any of that second category, the lone pairs. We have just these kind of sets. And so the way that we get those 2 sets as far apart as we can possibly get them is like this. Well, let's look at how we did that. Okay, we should start out with the electron dots. Okay, so this is the electron pair shape, and it's called linear, straight line. Okay, and we put the atoms on there, we get that. So it looks a lot like that, but we don't have the triple bond or the lone pair sitting out here. That's the shape of the molecule. Linear molecular shape. Linear electron pair shape, then linear molecular shape. Okay? So I'm going to give you a molecule now. I'm not going to tell you which of these type of geometries you're going to need. You're going to have to figure it out. Okay? Everybody ready? You did a balloon model of this. It's homework, or you should have. See if you can figure out the shape of this. Okay? So let's look at CO2. Carbon has 1, 2, 3, 4 valence electrons. Oxygen has how many? 6. 1, 2, 3, 4, 5, 6. And I need 2 oxygens, right? I'm going to do this kind of funky just so in case you guys have been struggling with where you put these things. Well, I kind of know where they're going in the first place. And I might be making the mistake of, writing it out in the order it's going to go to anyway. But, you can have them listed anywhere and still share electrons. That's what I'm going to show you here, okay? So I can share an electron between this carbon and this oxygen, and this carbon and this oxygen. And you might try to share electrons in a way that doesn't really work out very well, but you can change that. You can try it more than once. All right? That means that if you try it one way, it doesn't quite work out, try it another way. Okay? Go back and punt. Just because you don't get it the first time doesn't mean you won't be able to get it if you do it the second or third or fourth or fifth time. keep playing with it until you get it right. Okay? Keep up with your drawings. So when you look at the first one, don't go back to the 5th time and do the same thing. That's the definition of insanity according to Einstein, doing the same thing more than, repeatedly and expecting different results. Okay? Keep your drawings there and look and try something different until you get the right drawing. Okay? Even chemists have a hard time with this stuff sometimes. There are molecules, or polyatomic ions too, where just drawing it out the way we do it in here won't give you the right drawing. You have to do some math to figure out what the right drawing is. If you have more than one that can be equally reasonable, you do some math to figure out which is the right one to do. Okay? And even that, sometimes it predicts pretty well, but sometimes it isn't the most, sometimes it's actually off a little bit. Even the math doesn't work out. You have to do some experimentation to see which form actually works out the best. Okay? So this stuff gets more complex as time goes along. That's the beauty of science. You never stop learning. Every time you get an answer to something, there's more questions. You get more stuff to learn. Anyway, all right. So now I can share this electron with this carbon. Okay? And I can share this electron here with this, between this carbon and this oxygen. Okay? Now, actually this should have gone around that one. That should be left alone there. But the point is that we have 2 electrons shared between carbon and oxygen, and 2 electrons shared between carbon and oxygen. Okay? So our electron dot formula then looks like this. I'm sorry, the Lewis dot formula looks like this. Okay? Now from this then we can go draw a 3-dimensional shape. So carbon is here, and what angle is going to get those 2 sets of electrons as far apart from each other as we can get them? A straight line, which you call linear. Okay. There's our linear electron pair shape. Then we're going to redraw the exact same shape in pencil. And we're going to say, okay, this set of electrons, that's shared. So I need to put that atom over here. I'm going to draw an oxygen here. And this set of electrons here, that set right there, they're shared between this oxygen and this carbon. So I'll put an oxygen over here. Okay? And that's the molecular shape for carbon dioxide. And it's a linear molecular shape. Okay? Any questions about that? All right, so this is a model that somebody made of a, so I can get on the screen just right, okay, of a molecule of CO2. And if the balloons are really tightly pulled together, which they should be, because these bonds are actually coming out of the nucleus here, okay, pull them really, really tight together, then these pi bonds make it form this linear shape, okay? You got a sigma bond in the middle, so this is a sigma bond here, and a pi bond with the top and bottom parts, because pi bonds look like they're in 2 parts. So this is a double bond here. You got 2 lone pairs out here on the end where the oxygen is. Same on the other end. Okay. If all these were pulled really, really tightly, this would be a nice molecule that would actually give you the shape of what CO2 looks like. But this pulling in tight like that, okay, that you can't twist it around. You can't wiggle it. Basically that has to have that shape, which is what those electrons do in this molecule. Those electrons push apart from each other and keep this thing from being any other shape other than this. Does that make sense? That's the reason we do balloon models, so you can actually see the results. If you're not paying attention to it, if you do it at home, take a picture of it or bring it in and throw it away, and you're not thinking about what this is actually showing you, you're not getting everything out of it you possibly. All right, what I want to do is to show you how we get the shape of some ionic compounds. Okay, so that's what we're going to do here. And I'm going to start with a really simple one, sodium chloride. Okay, before I do that, I want to show you how we get to these charged particles here using orbital notation. Okay. All right. So if I have a sodium atom, here's a sodium atom, and I look at its place on the periodic table to tell me something about what its orbital notation is going to be, I'll see that sodium is in the third primary energy level, so the first two energy levels are completely full. So 1s is completely full, 2s and 2p are completely full, and so we've got one electron in 3s. Okay? Now this is a metal. All the atoms on the left-hand side over here of the periodic table, including sodium, left-hand side of this stair step here, all these atoms over here are going to be metals. Yes? Well, that's what we're going to be showing you is the structure of salt when we get there. Okay, I'm going to show you how to figure that out, what it is that makes sodium have the structure it has. Sodium chloride, table salt, have the structure it has. And so do all metal-non-metal combinations do kind of the same thing. All right, and that's what we're doing here. We're just starting with something fairly simple. Now, chlorine is on the same row of the periodic table, but it's way over here on the right-hand side. It's a non-metal. It's on above on this stair step here. It's over here. All these over here are non-metals. Okay. I sure hope you're taking notes on all this. Okay. Now in covalent bonding, what happens is that electrons are shared and fill up these orbitals. Okay? When I'm combining a metal with a nonmetal, that is not what happens. With covalent bonding, you mostly have p sublevels that are partly full, and we hybridize to be able to completely fill those. Here, the sodium doesn't even have a p sublevel in its valence level. So what sodium is going to do, or one way you can think about it to figure all this out, I'm not sure that it actually happens this way. It probably does, but I couldn't say for certain that it happens this way. What is actually going to happen when you're bonding a metal and a nonmetal, it actually happens when you do polyatomic ions. We're not going to get into that until later. We're going to look at something fairly simple. This electron actually leaves. So this electron in 3s, it's going to go away, and it's going to go down here and join up in the orbital of chlorine. Okay? So this electron is gone completely, and now we have a full outer energy level for chlorine. Oh, but wait. We have a full outer energy level for sodium now, don't we? Okay? So both of these atoms now have an outer energy level that's completely full, fulfilling that octet rule. That makes sense? All atoms want to have a full outer energy level of 8 electrons. That makes sense to you? See? So, now you got to know the difference. One of the things that just, I scratch my head over this stuff when we get to a test is, I give people two atoms or a formula and say, okay, give me the orbital notation for this. And they'll do covalent bonding for something that's clearly ionic. A metal and nonmetal is going to be ionic. They're going to exchange electrons. Okay? And then I'll give them a molecule and they'll do ionic. What's the deal with that? All right? So make sure you understand. If I'm combining nonmetals, they share electrons. If I'm combining a metal and a nonmetal, or more than one metal and nonmetal, they're not sharing electrons, they're giving up and taking, okay? These guys don't play well together. Chlorines steal the electrons and go home. That's not nice, okay? You got to know it's a metal and nonmetal combination, so it's an ionic bond. What we have here is we've taken an electron away from sodium, okay? Sodium originally had the atom of sodium had 11 protons and therefore 11 electrons. But it lost its electron on the outer energy level. What does that mean? It's got one more proton than electrons now in this form. What does that mean about the charge on the sodium? It's now positive. And you have to show a positive charge there because it's positive. If it's lost an electron, it's a positive charge because it has one more proton than electrons. It's got 11 protons and only 10 electrons. Okay? You have to know that. If I lose 2 electrons, what does the charge become? 2 plus. If I lose 3 electrons, what does the charge become? 3 plus. If I gain an electron, as chlorine did here, what charge does it have? A negative 1. Okay? So chlorine has 17 protons and 17 electrons. Now it has 18 electrons. And if you remember when we're doing the periodic table regions and the periodic table patterns in the last unit, we said that chlorine has a high, it's over here in this end of the periodic table, where it has a high electron affinity. It wants to take electrons away. So it pulls the electrons away from the sodium. And the sodium has a low electron affinity. Okay? It gives up those electrons. So when we take an electron away from sodium, we put energy into sodium. But when we put that electron on chlorine, it gives up some energy. So it's kind of a wash. Yes? So, this is the orbital notation. Let's look at electron dots. Draw the electron dot notation for both a sodium atom and a chlorine atom. Draw the electron dot notation for a sodium atom and a chlorine atom, and then we'll see how you did. Here. So, sodium's electron dot notation will have how many electrons? How many dots? How many electron dots does sodium have? Just 1. Okay, how many electron dots does chlorine have? 7. 2, 3, 4, 5, 6, and 7. That's before we put this extra one in here. Okay, so chlorine has 7. Okay, so in this drawing, in orbital notation, we showed how the electron left here and went to here. We're going to do that same thing here. This electron is going to leave here and go there. Okay? Then we're going to draw a new drawing that shows the result after it leaves. This is what it's going to do. Now we're going to show what it actually does at the end. So sodium now has no electrons. And since it has no electrons, it has what kind of charge? Positive. Okay? And chlorine started out with 7 electrons, and now it has 8. So what charge does it have? Negative. Now the critical thing is that it's important that you know that this negative charge is shared over this entire chlorine structure. Okay? And so we're going to put a bracket here to show this negative doesn't just apply, say, to those electrons or something. The bracket tells you because the negative charge is on the outside, it shows it applies to the whole thing. You could put a bracket around sodium, but it's not really necessary because with sodium, you don't have any electrons showing over. There's only one symbol, so it's not like there's any confusion. Does that make sense? Okay. Any questions about that? How that works? Okay. So now you guys can try this. Let's see. Let you try. How about magnesium and fluorine? I'm going to let you put together magnesium and fluorine, and in doing so, figure out how many magnesiums and or fluorines you actually need to make it work out.
So you're going to do the orbital rotation?
Well, yeah, I want you to do the orbital notation and the electron dot formula, and do it in pencil in case you have to erase, and then see how you come out. I'm going to do it behind you. Okay, give everybody a chance to practice a little bit. Let's check it out then. See how you did. So how many electrons? Well, let's do the orbital notation first. Here's magnesium. And magnesium is on the 3rd row of the periodic table. So we're going to fill up the first row the first level, the second level, and we're going to only put 2 electrons in the third. So the second level is going to have s and p electrons and orbitals. And so when we get to 3, the third level, there's only an s sublevel, 3s, and 2 electrons there. Fluorine is on the second row, and it's going to have 2 electrons in 2s and 5 electrons in 2p. Two, 3, 4, 5. Okay, and so we want to work it out so that magnesium has a full outer energy level, and that fluorine also has a full outer energy level. So what am I going to do? Add some more whats? Add some more electrons? Okay. Well, let's see. I need to get rid of how many electrons from magnesium? It's the metal. Just 1? 2? 2 of them. Okay. So if I take this one right here and I move it down here, that takes care of fluorine. It now has 8 electrons in its outer energy level, yes? And it has a negative charge. Magnesium has a plus charge, but it still needs to lose an electron. What do I do? Huh? Add another fluorine. Yeah, add another fluorine. And so now the second electron here in the third primary level can leave and come down here. And now magnesium is not just a plus, a 1 plus, it's 2 plus because it's lost 2 electrons. Okay? And both these fluorines have a negative charge because they both have gained 1 electron. And the overall compound is charge balanced because it got a 2 plus here and 2 negative charges to balance it out. That makes sense? Okay? Can you do the electron dots? Try that. We're going to pause the video again, let you work on the electron dots. Alright, so magnesium has how many valence electrons, and therefore how many electron dots does it have? 2. 1, 2. And how many electron dots does fluorine have? 7. 1, 2, 3, 4, 5, 6, and 7. And so 1 electron here can go over here and leave and go to fluorine, and that takes care of fluorine. Fluorine's happy, and that's personifying fluorine. You know, fluorine's not alive, so it's not really happy. But we sometimes call it that because it makes it easier for us to understand. But we need another fluorine so we can get rid of that other electron on magnesium. And so then this electron is going to go over here. Okay? And then we're going to show the result, just like a comic book, guys. Here's panel 1, okay? Up here, it's panel 1, and then panel 2, going from one to the next, okay? We're just telling a story. We're doing the same thing here. Here's panel 1. And here's panel 2. And magnesium has lost 2 electrons, so it has what kind of charge? 2 positive, okay? And you got 2 different fluorines, and there's 2 ways to write this, okay? One way to write this is to show a fluorine that has a full valence level, and this one fluorine has a negative charge, and then we've got another fluorine with a negative charge, okay, and that will be fine. That's perfectly okay to do it that way, okay. But it's also okay when you get good at this, to write it like this. All right. If you're sure of yourself, sure enough of yourself to do that, you can do that. Okay? Huh? No, we're just saying there are 2 fluorines. All right. Now, the result then is we know now the formula for sodium chloride. Don't throw things in class, please. You were both throwing things. Okay? And so this is 1 sodium and 1 fluorine. This down here is 1 magnesium and 2 fluorines. Does that make sense? Any questions? All right then, let's give you some homework to practice. Oh!